the first thing we're going to talk about today is arithmetic sequences when they are written in explicit form. So remember that there's two different types of sequences we've talked about. We've talked about arithmetic sequences, which means to do what? Add or subtract. We've also talked about geometric sequences, which means to do what? Multiply and divide. Perfect. Those are two very separate things when we're talking about this. So if you're given a table, you're going to see numbers being added every single time. If you're given a table, maybe you'll see numbers being multiplied every single time to get from one y value to the next. If you're given a graph, do you guys know what the difference would look like graphically? What would a graph of an arithmetic sequence look like? Linear, a straight line. What about the graph of a geometric sequence? Exponential. Good. It's that one that looks like the big curve. That's called an exponential function. So the first thing I want to look at is an arithmetic sequence when it's written in explicit form. So remember that there are two forms of how we're going to write arithmetic sequences. The first form looks like this. F of n equals, and you can use one or the other of these two functions. So the first one is f of n equals f of 0 plus dn. Now, get out a highlighter for me if you don't have one out, because I'm going to have you highlight a couple things for me. All right, the reason I'm having you highlight these is as follows. When I graded your most recent quizzes, I noticed that a lot of you guys weren't sure like what you're supposed to replace in the equation and what's actually supposed to stay in the equation as is. So this whole f of 0 idea, some people like replace the f and then they put some number times 0, or some people replace the 0 and they put like f of some number. And it was getting confusing because you weren't really quite sure what part of the equation you were supposed to be replacing. So the things I've highlighted are the things you should be replacing in the equation. So let's do an example together. So I'm going to write down an arithmetic sequence and we're going to plug it into this equation. So write down the sequence with me. Let's go 0, 3, 6, 9, 12. So remember, there's two ways we can write this arithmetic sequence in explicit form. The first way is by leaving it like this, but that's the second equation that we're going to get to in just a second. The other way is to go back to the 0 term. All right, f of 0 is the 0 term. This is not the 0 term. I know it equals 0, but it's not the 0 term. This is the first term. How do we go back to find the 0 term? Subtract by what we're doing. So what are we doing to get from 1 to the next every time? Adding 3. So this time we're going to subtract 3 to go backwards. That would be negative 3. So our 0 term, or our initial term, is negative 3. And again, this is just one option if you want to do it this way. You don't have to do it this way. It's just an option if you want to do it this way. Remember, there's two forms you could write it in. So we could write it like this. F of n equals, the 0 term is negative 3 plus d is the common difference, what we're adding every single time. You guys said that was 3 times n. And then let me highlight to show you guys that those are the things we replaced. So notice that I didn't write f of negative 3 for the 0 term. I just wrote negative 3. So you're replacing that entire thing. F of 0 just means what is the initial term. So when you get your quizzes back today, maybe you'll notice that. Maybe you accidentally left the f in there and you didn't mean to leave the f in there. So make sure you replace it like that. All right, the other form. So this is one form. I'll put a box around that. The other form of an arithmetic sequence in explicit form looks like this. F of n equals, you can also start from the first term and add d n minus 1 times. That's the other option. So remember, in this case, instead of having to go back to the initial term, you can stay at the first term, which is what in this case? What was the very first term in this purple sequence? 0. So you can stay at the first term, which is 0. And add 3 n minus 1 times. So those are the two options for how you could write an arithmetic sequence. You do not have to write both. So if it just asks you to write the arithmetic sequence in explicit form, you can choose one or the other. You do not have to choose both. Yes? You could just put 3 times n minus 1. That's totally fine, yeah. So the other option, though, if it's not asking you to explicitly write it, like giving you the option of which one to choose, maybe it's a multiple choice or maybe it's a matching one, you need to be able to recognize both. So remember, the options are go back to the 0 term and add d n times, or stay at the first term and add d n minus 1 times. And these posters, by the way, I know I told you I was going to take them down for the test, but I'm actually going to leave them up for the test. So I'll leave them here, and I will also project them on the board, just like we did for your quiz. So my main concern is that you know how to use the equations and plug in things where they need to be plugged in. All right, arithmetic sequences. Questions about arithmetic sequences written in explicit form? All right. Then I want to go to geometric sequences written in explicit form. We'll come back to arithmetic written in recursive form. So now we're looking at geometric sequences that are written in explicit form. So geometric, remember, means to do what? Multiply and divide. Sequences that multiply and divide. Let's look at the two forms for geometric. Form number 1, f of n equals. Again, we can start at the 0 term. If we go back to the 0 term, f of 0 times, in this case it was r for common ratio, to the power of n. Or we can go back, or I'm sorry, that was going back. Or we can stay at the first term, f of 1 times r to the power of n minus 1. So remember, your two options are go back to the initial term and multiply times r to the power of n, or stay at the first term and multiply times r to the power of n minus 1. So if you don't want to go back in the first term, you have to go back in the exponent. And let's do an example. Let's do this. 5 times, let's do this one, then this one, dot, dot, dot. All right. What am I multiplying by every single time to get from 5 to 15 to 45? Times 3. So to go back to the initial term, I'm going to do what? Divide by 3. What's 5 divided by 3? 5/3. Good. I do not need a decimal. You can leave it as a fraction. Leave that as 5/3. Our two options, therefore, are, if we choose the first function, we can rewrite it as going back to the initial term, which is 5/3, times the common ratio, which is 3 to the power of n. That's option 1. Option 2 is we can stay at the first term. What was the first term in this green sequence before I went back to the initial term? 5. We can also stay at 5 and multiply by the common ratio n minus 1 times. So again, those are your two options for how you can write a geometric sequence in explicit form. Go back to the initial term, multiply times r to the power of n, or stay at the first term and multiply times r to the power of n minus 1. Those are your two options. And again, notice how we're replacing all this. F of 0 gets replaced by what the initial term is. F of 1 gets replaced by the first term. R gets replaced by 3 in both of these. So you shouldn't have, in explicit form, you shouldn't have an f anymore over there in your equation. I mean, of course, you have f of n equals, but on the right-hand side, you don't have an f anymore. The whole f of 0 is the entire first term, and it replaces that entire f of 0. All right. Now, let's go back to recursive form, because a lot of you guys need a little bit of a hint or a little bit of a reminder about how we write recursive form, because a lot of you guys on your test forgot some crucial pieces of it, and I want to make sure that you guys are clear on how to look at those crucial pieces. So let me undo this, and let's go back to this. Arithmetic sequences written in recursive form. There are two things you need in order to write a sequence in recursive form. You need to state one of the numbers. So usually we start at the first number. We'll tell them the first number of the sequence is blank. And then we tell them for every number after that, or for every term after that, we're always going to multiply it by a certain number. Or in this case, since it's arithmetic, we're always going to add by a certain number. So let me write a sequence first, and then we can come up with the recursive formula. So let's do the sequence 4, 10, 16, 22. Turn to your neighbor next to you and tell them, what are we adding by every single time? All right, now tell me, what are we adding by every time? 6. So we're saying plus 6, plus 6, plus 6, plus 6, like that. Perfect. Now here's how we write this in recursive form. So recursive is always like, given this one, what's the one right before it kind of thing. So we always tell them what the first term is. So write this with me. We say f of 1 is equal to, what is the first term in the sequence? At the purple numbers up at the top, what's the first number in the sequence? 4. That's the first thing you always have to put for recursive. If you forget that, that's a big part of recursive, so don't forget to write that. And then the next thing you need to tell them is to find any number in the sequence, f of n. We always take the number right before it. So the number right before f of n would be f of n minus 1. And we do what to it? So to get from 4 to 10, what do we do? Add 6. To get from 10 to 16, what did we do? Added 6. To get from 16 to 22, what did we do? Added 6. So to get from any number to the next, so f of n is the next number, f of n minus 1 is the one right before it, we always add 6. Notice that this is the only thing that's changing in the equation. That plus 6 is the only thing that's changing, as well as this 4. Those are the only two things you're adding to your equation or changing in your equation. Everything else stays exactly the same. Yes, sir?
What happens when it gives you that and then it goes like greater than equal to 1 or 2?
Great. So the other part of this that is more notationally, and so it has to do with the whole making sure that the function actually works, is that they'll add on a little thing to the end of this that says n has to be greater than or equal to 2. The reason they say that is because they're letting you start at 1, so the only numbers you can plug into this equation are numbers that are greater than 2. Because if you try to plug in 1 to this equation, what happens when you do 1 minus 1 over here? 0, so f of 0. But we don't know what f of 0 is. They're starting us at f equals 1. So essentially this notation is just to let you know, hey, we don't know what f of 0 is, we only know what f of 1 is. So you have to start at numbers greater than or equal to 2 so that you can go up from there. So 2 minus 1 would be f of 1, and that's the first number we know in our sequence. So that is strictly notational, so to help you understand the mathematics of the notation. Any other questions about recursive form for arithmetic sequences? A couple things I noticed, by the way, a lot of you guys were changing like the 1 in here. You change it to like n minus 4, you changed them to random things on your quizzes. This always stays the same. So this part of the function, this part of the function, and this part of the function never change. In a recursive formula, you're always going to see those exactly the same. The only thing that changes is what I've highlighted. So you're either changing what the initial term is, or changing what you're adding by, or changing what you're multiplying by. Everything else is exactly the same. Yes?
So the f stays in the equation for every single?
Which one? This one or this one?
That one.
Yes, this one for recursive form will always be there. So you remember how we were just talking about with explicit form, how the f of 0 should go away and be replaced by the initial term? This is part of the equation in recursive form, so this always stays there. So your recursive form equations will always have f of n minus 1. The only thing that changes is this plus 6, or maybe it'll be times 3, or maybe it'll be divided by 1/2 or something, or times 1/2, so on and so forth. Any other questions about arithmetic recursive sequences before we look at geometric? Yeah?
Does that have to be on it? Like,
The n greater than or equal to 2? I would be more concerned with you recognizing when it's written on your test than you physically writing it on your test. That would be a perfect answer, but I will not mark you wrong for not putting the n greater than or equal to 2. The other two parts are the most important to me. All right. Any other questions on this one before we try geometric? Great. Let's look at geometric then. So these are geometric sequences in recursive form. So let's see. Let's come up with some numbers. What do you want your first number to be in our sequence? 5. And what should we multiply by? 2. So that's 5, 10, 20, 40, so on and so forth. So, again, geometric and arithmetic recursive sequences look very, very similar. For geometric sequences, the notation is exactly the same. We still have f of 1 equals f of n equals f of n minus 1, and then dot, dot, dot. So remember how I told you guys in arithmetic sequences that these things are always in the equation? That's also true for geometric sequences. Those things are always in your recursive equations. The only thing that changes is what the first term equals and what you're doing to the number right before it to get to the next one. So in this sequence, what's our first term? 5. So I want you to write f of 1 equals 5. That's what will change. The first term will change. If it's 7, you'd put 7. If it's 15, you'd put 15, so on and so forth. And then the only other thing that changes is I want to know what we're doing to every term to get to the one after it. So what are we doing to 5 to get to 10? Times 2. What about from 10 to 20? Times 2. What about from 20 to 40? Times 2. So the only thing that changes is that I'm going to write a times 2 right there. That's the other part that changes. And then again, if we want to be perfect notationally, we'll say that n is greater than or equal to 2. Some people were asking me, this 2, does it have to be at the back? Can it be at the front? Absolutely. You could put 2 times f of n minus 1, or you could put f of n minus 1 times 2. It does not matter what order you put it in. Yeah. Multiplying numbers, you can do in either order. Okay. I know that was a lot. Those are all of the equations we've learned so far for arithmetic and geometric sequences in recursive form and explicit form. At the end of the period today, we're going to practice converting between them, because I know that some of you guys have difficulty sometimes recognizing the differences and similarities between them, so we're going to practice with that. But that's essentially the basics of how to write them. Questions about that? All right. So the next thing I want to look at is writing exponential functions from a table. So let me write a table up here on the board, and you guys can copy it down. So sometimes I'll give you a sequence of numbers. Sometimes I'll give you a table of numbers, and we have to write the exponential function from a table of numbers. Now, it still holds true that we could write these as like sequences in their sequence forms, but typically when we start moving into exponential functions and not just sequences, typically we're only going to use the one that looks like a times b to the power of n. You remember that one? Let me write it up here in the corner. Y equals a times b to the power of x. I think I said n. I meant x. What does the a represent? Yeah, the 0 term. Or, if we were looking at the graph, it would represent the y-intercept. What does the b represent? What you're multiplying by, your multiplier. Notice the differences and similarities, I should say, between this equation and then the one written in explicit form for geometric sequences. So in explicit form, this said f of 0 times r to the power of n. We have that right here on this poster. F of 0 times r to the power of n. This is the exact same equation. It's just this notation we use when we're talking about sequences. So f of 0 is your initial term, just like a is our 0 term, or our y-intercept. R was our common ratio, just like b is our multiplier. So that's what you're comparing it to. The difference is that with sequences, I'll just tell you numbers, like this number, then this number, then this number, then this number. Versus with exponential functions, we could actually graph them and create a function from it. We call that continuous versus discrete. Sequences are discrete. Exponential functions are continuous when we graph them. All right, so look at this chart and turn to your neighbor next to you. I want you to tell them what a is, what the 0 term is, and tell them what b is, the multiplier. So who can tell me what a is? What is the initial term? 32. A equals 32. Some of you guys have been choosing the one across from -1 just because it's the first term in the table. That's not always true. The first term in the table is not always the initial term. In this case, it's the negative first term. And then here, some people have been choosing across from 1, and they'll choose 16. That is not the initial term either. The initial term is always right across from 0, so 32. What about b? What are we multiplying by to get from 64 to 32 to 16 to 8? 1/2. Good. Divided by 2, which is the same thing as times 1/2. Perfect. So when we plug these in the equation, we get y equals 32 times 1/2 to the power of x. Final answer. Notice that I have to put 1/2 in parentheses. If you do not put 1/2 in parentheses, it will be incorrect, because that would not imply that the x goes to both the top and bottom of that fraction. All right. So from a table, here's how you write the equation. Find the zero term, find what you're multiplying or dividing by every single time, and write it in that form. Did you notice in your Socrative that there were some like that, but with arithmetic?
Yeah.
We weren't multiplying and dividing, we were actually adding and subtracting. It looks very similar to this. The only difference, you still look for the zero term. The only difference is that instead of being in this form for exponential sequences, you would just write it in the form for arithmetic sequences, where it's the initial term plus the common difference times x. So for those ones in your Socrative, you'll notice that it looks like a linear equation rather than an exponential equation. All right, what about writing exponential functions from a graph? Let me graph this for you. Oops, I probably should write these both as coordinates. Say it again? Yes, so this one we're going to look at writing exponential functions from a graph rather than writing exponential functions from a table. All right, so I'm going to give you guys a minute. I want you to turn to your neighbor next to you. I want you to tell them what A is, so what's your initial term or your y-intercept, and tell them what B is, what you're multiplying by every single time. All right, let's look at it together. So A is your initial term or your y-intercept. Everybody shout it out to me. What's the y-intercept in this problem? 3. This is the y-intercept right here. It's where it crosses the y-axis. So A is equal to 3. Now, when we go over 1 unit, we go up to 9. So to get from 3 to 9, what am I doing? Multiplying by 3. So my common ratio is 3. So when I write this equation, it's A times B to the power of x. That's 3 times 3 to the power of x. Now, again, notice that the shape of this function is exponential. It's that curved shape. Sometimes, and I think you had this in your Socrative as well, sometimes it's not that curved shape. Sometimes it looks like a straight line. So if it was a straight line instead of a curved shape, so for example, let me do it in red. Let's pretend it looked like this. Oh, that's not quite right, isn't it? Try that again. Like that. Ooh, that's nice. Perfect. All right, let's say that it was this red function instead of the purple function that I had graphed. We wouldn't be multiplying and dividing every single time. What would we be doing then? Adding and subtracting. Perfect. Notice that my y-intercept is the same. The y-intercept is still 3. So if I was going to write this function, it would be y equals 3. What am I adding to get from 3 to 9? 6. So plus 6x. So notice the differences. If it's a straight line, you're looking for an arithmetic sequence where it's adding and subtracting. If it's a curved line, like an exponential function, the purple one, you're looking for a geometric sequence where you're multiplying and dividing. So notice the differences. I can connect these 2 points with both types of lines. With one of them, I get an exponential function. With the other one, I get a linear function. So notice the differences between those and the similarities between them. All right, there's one more thing we're going to talk about from this unit before we go back and start reviewing things from old units. And the last thing that I want to talk about from this unit is writing exponential functions from a situation. All right, so I'm going to just briefly say the situation rather than writing it out word for word, and then we'll write down and jot down what's important from the situation. You ready? All right, let's say that I have a brand new car. I just bought a brand new car back in 2010. Okay, so I'm going to start jotting down things that are important. So I have a car. I bought it in 2010. That's not a year, is it? 2010. How much money did I buy my car for? What do you think?
A lot.
How much is a lot? Did you say 50,000? Gosh, I'm not that rich. Let's say 20,000. How about 20,000? That's a good starter car. All right, you bought your car in 2010 for $20,000. Let's say that cars, because they don't hold their value, let's say that cars depreciate. What does the word depreciate mean? To decrease. Let's say that cars depreciate by, so it depreciates. Let's say that it depreciates by 10% every year. And let's say I want to sell it this year. So I've had this car now, and I want to sell it this year in 2018. I want to know how much my car is worth this year. How much should I sell it for? If it's perfect condition, I've taken amazing care of it, it's never been in an accident, so on and so forth. How much can we sell it for? So let's create an equation. We need to know our A value and we need to know our B value. And from there, we can put it into an equation. So our A value is our initial term or our y-intercept or where we're starting. So how much is my car starting at? 20,000. So I want you guys to say A equals 20,000. Now for B, remember that for B, we start at one whole, right? We have one whole amount for this car. It's at 100% when we start. And we either go up if it's gaining value or down if it's losing value. Is my car gaining in value or losing in value? It's losing in value. So we're going to start at 1, and we're going to lose in value by how much every year? 10%. How do I write 10% as a decimal? 10%. I'm doing this for demonstration purposes. 10%, if I move the decimal place twice, is 0.1, 0.1. Good. So B is equal to 0.1 or 0.1. So what is 1 minus 0.1? 0.9. Good, or 0.9. So if it loses 10% of its value every single year, then it means it keeps 90% of its value every year. So let's write our equation. Y equals A, which is 20,000, times B, which is 0.9, to the power of X. And in this example, what is X? How much time has passed from 2010 to 2018? 8 years. So I can just plug in 8 for that. So do me a favor, get out a calculator really quick and figure out, you can use your cell phone calculators for right now. Figure out what 0.9 to the power of 8 is, because we do exponents first, and then multiply that times 20,000. All right, who can tell me what they got for this one? Yeah.
$8,609.36.
All right, does that sound right to the rest of you guys? Perfect. So if I hold on to my car for 8 years, it's only worth $8,600 now. So cars are necessary, but maybe not the best investments because they don't hold their value very well, depending on which car you get. And sometimes they can gain in value. I think we've talked about that as well, if you get a collector car. All right, so we have reviewed the following today. Given an arithmetic or geometric sequence, how do you write it in explicit form? How do you write it in recursive form? How do you write an exponential function from a table, from a graph, from a situation? These are all things that you are expected to know for your test tomorrow. In addition to this, however, there are other things that you are expected to know relating back to things from old units, which I would like to talk about now. So let's transition for just a minute and talk about some stuff from an older unit.